If you look past the edge of our sun's influence, the absolute closest star to Earth is a red dwarf called Proxima Centauri. Astronomers used the radial velocity method, tracking how a star's light shifts, to discover 3 planets in orbit, B, C, and D. Calculations show planet B has almost exactly the same mass as Earth, making it a critical starting point in our search for life. Finding Earth-mass worlds right next door makes this system the ultimate destination for our curiosity. It is the first place we would go if we could only find a way to cross the gap. We have known Proxima Centauri was our neighbor for over a century. In 1915, astronomer Robert Innes measured its parallax, proving it was physically closer to us than the Alpha Centauri binary stars. Innes confirmed this by comparing physical glass photographic plates, manually tracking how the star's position shifted against the background of space over several years. But in space, close is a relative term. While it is our nearest neighbor, that distance still totals over 40 trillion kilometers. This creates an astronomical illusion. Proxima Centauri is close enough to see and study, but the sheer physical distance keeps it trapped just out of reach of our current technology. Crossing 40 trillion kilometers in a reasonable time frame requires a constant speed that is impossible for standard chemical rockets. They simply cannot carry enough energy to sustain the trip. This is the rocket equation's central problem. To go faster, you need more fuel, but fuel has mass, requiring even more fuel just to move it. Eventually, the weight of the fuel prevents the ship from accelerating. Even advanced concepts like the Vasimer rocket can't solve this. While it accelerates ions efficiently, it still requires heavy propellant tanks. Dragging that mass across the void remains a brick wall. To reach the stars, we have to change our strategy entirely. We have to leave the fuel and the engine behind on Earth and find a way to push the spacecraft from a distance. Our exploration is stalled not by a lack of raw engine power, but by the physical impossibility of carrying that power with us into the vacuum. This realization led to Breakthrough Starshot. It is a proof-of-concept project designed specifically to solve the mass problem by separating the probe from its propulsion. The project carries immense scientific weight, with backing from prominent technologists and the late Stephen Hawking. Their solution is a light sail. It involves attaching a payload the size of a microchip to a square of razor-thin, highly reflective material. Instead of an onboard engine, a massive laser array on the ground fires a high-powered beam into space. When those photons hit the sail, they transfer their momentum and push the probe forward. Because the probe is so light, this external laser can accelerate the chip to 20% of the speed of light, fast enough to reach Proxima Centauri in just over 2 decades. By decoupling the energy source from the craft, we finally have the velocity required to cross the interstellar void. But even with the right speed, the environment of the void is incredibly hostile. Traveling at 20% of the speed of light turns even the smallest particles into lethal threats. At these speeds, a collision with a single microscopic grain of dust or a blast of UV radiation would vaporize a microchip instantly. The very velocity that gets us there also makes the spacecraft extremely fragile. Speed solves the problem of distance, but it also increases the vulnerability of our probes. Every kilometer traveled is a gamble against total destruction. Reaching Proxima Centauri means we have to abandon the idea of massive human-crewed ships we see in science fiction. Our biology and the weight of our life support systems are simply too heavy for the trip. The future of interstellar travel belongs to swarms of uncrewed laser-propelled microchips. We may send thousands of them, hoping just a few survive the journey to send data back. We have the engineering potential to finally touch the stars, but to reach them, we have to accept that our physical bodies will remain here in our own solar system.